today we're going to go over these 4 major software packages that people commonly use for deep learning. As usual, a couple administrative things. The milestones were actually due last week, so hopefully you turn them in, and we'll try to take a look at those this week. Also remember that assignment 3, the final assignment, is going to be due on Wednesday. So any of you guys done already? OK, that's good. And you have late days, so you should be fine. Another thing that I should point out is that if you're actually planning on using terminal for your projects, which I think a lot of you are, then make sure you're backing up your code and data and things off of the terminal instances every once in a while. We've had some problems where the instances will crash randomly. And in most cases, the terminal folks have been able to get the data back, but it sometimes takes a couple days. And there's been a couple of cases where actually people lost data because it was just on terminal and it crashed. So I think if you are planning to use terminal, then make sure that you have some alternative backup strategy for your code and your data. So like I said, today we're talking about these 4 software packages that are commonly used for deep learning: Caffe, Torch, Theano, and TensorFlow. And as a little bit of disclaimer at the beginning, personally, I've mostly worked with Caffe and Torch. So those are the ones that I know the most about. I'll do my best to give you a good flavor for the others as well. But just throwing that disclaimer out there. So the first one is Caffe. We saw in the last lecture that really Caffe sprung out of this paper at Berkeley that was trying to re-implement AlexNet and use AlexNet features for other things. And since then, Caffe has really grown into a really, really popular, widely used package for especially convolutional neural networks. So Caffe is from Berkeley, that I think a lot of you people know. And it's mostly written in C++. And there's actually bindings for Caffe, so you can access the nets and whatnot in Python and MATLAB that are super useful. And in general, Caffe is really widely used, and it's really, really good if you just want to train sort of standard feed-forward vanilla convolutional networks. And actually, Caffe is somewhat different than the other frameworks in this respect, that you can actually train big, powerful models in Caffe without writing any code yourself. So for example, the ResNet image classification model that won everything last year, you can actually train a ResNet using Caffe without writing any code, which is pretty amazing. So the most important tip when you're working with Caffe is that the documentation is sometimes out of date and not always perfect. So you need to not be afraid to just dive in there and read the source code yourself. It's C++, so hopefully you can read that and understand it. But in general, the C++ code that they have in Caffe is pretty well structured, pretty well organized, and pretty easy to understand. So if you have doubts about how things work in Caffe, your best bet is just to go on GitHub and read the source code. So Caffe is this huge, big project with probably thousands, tens of thousands of lines of code, and it's a little bit scary to understand how everything fits together. But there's really 4 major classes in Caffe that you need to know about. The first one is a blob. So blobs store all of your data and your weights and your activations in the network. So these blobs are things in the network. So your weights are stored in a blob. Your data, which would be like your pixel values, are stored in a blob. And your labels, your Ys, are stored in a blob. And also all of your intermediate activations will also be stored in blobs. So blobs are these n-dimensional tensors, sort of like you've seen in NumPy, except that they actually have 4 copies of an n-dimensional tensor inside. They have a data version of the tensor, which is storing the actual raw data. And they also have a parallel tensor called diffs that Caffe uses to store gradients with respect to that data. And that gives you 2. And then you actually have 4 because there's a CPU and a GPU version of each of those things. So you have data, you have diffs, you have CPU, you have GPU. So there's actually 4 n-dimensional tensors per blob. The next important class that you need to know about in Caffe is the layer. And a layer is sort of a function, sort of similar to the ones you wrote on the homeworks, that receives some input blobs, Caffe calls inputs bottoms, and then produces output blobs that Caffe calls top blobs. So the idea is that your layer will receive pointers to the bottom blobs with the data already filled in, and then it'll also receive a pointer to the top blobs, and in forward pass, it'll be expected to fill in the values for the data elements of your top blobs. Then in the backward pass, the layers will compute gradients. So they will expect to receive a pointer to the top blobs with the gradients and the activations filled in. And then they'll also receive a pointer to the bottom blobs and fill in the gradients for the bottoms. And layer is this pretty well-structured abstract class that you can go, and I have the links for the source and the header file here. And there's a lot of subclasses that implement different types of layers. Like I said, a common cafe problem, there's no really good list of all the layer types. You pretty much just need to look at the code and see what types of CPP files there are. The next thing you need to know about is a net. So a net just combines a bunch of layers. A net is basically a directed acyclic graph of layers and is responsible for running the forward and the backward methods of the layers in the correct order. So this is, you probably don't need to touch this class ever yourself, but it's kind of nice to look at to get a flavor of how everything fits together. And the final class that you need to know about is a solver. So the solver is, we had this thing called solver on the homework that was really inspired by cafe. So a solver is intended to dip into the net, run the net forward and backward on data, actually update the parameters of the network, and handle checkpointing and resuming from checkpoints and all that sort of stuff. And in cafe, solver is this abstract class, and different update rules are implemented by different subclasses. So there's, for example, a stochastic gradient descent solver, there's an atom solver, there's an RMS prop solver, all of that sort of stuff. And again, just to see what kinds of options are available, you should look at the source code. So this kind of gives you a nice little overview of how these things all fit together, that this whole thing on the right would be a net. The net contains, in the green boxes, blobs. Each blob contains data and diffs. The red boxes are layers that are connecting blobs together. And then the whole thing would get optimized with a solver. So Cafe makes heavy use of this funny thing called protocol buffers. Any of you guys ever interned at Google? Yeah, fair number, so you guys know about this. But protocol buffers are this almost like a binary, strongly typed JSON, I sort of like to think about it, that are used very widely inside Google for serializing data to disk and for passing it over the network. So protocol buffers, there's this .proto file that defines the different kinds of fields that different types of objects have. So in this example, there's a person that has a name and an ID and an email, and this lives in a .proto file. .proto files define a type of a class, and you can actually serialize instances to human-readable .prototxt files. So for example, this fills in the name, it gives you the ID, it gives you the email, and this is an instance of a person that can be saved into this text file. Then protobuf includes this compiler that actually lets you generate classes in various programming languages to access these data types. So you can, after running the protobuf compiler on this proto file, it produces classes that you can then import in Java and C++ and Python and Go and just about everything. So actually, Cafe makes wide use of these protocol buffers, and they use them to store pretty much everything in Cafe. So Cafe, like I said, to understand, you need to read the code to understand Cafe. And Cafe has this one giant file called cafe.proto that just defines all of the protocol buffer types that are used in Cafe. So this is a gigantic file. I think it's a couple thousand lines long, but it's actually pretty well documented and is, I think, the most up-to-date documentation of what all the layer types are, what the options for those layers are, how you specify all the options for solvers and layers and nets and all that. So I'd really encourage you to check out this file and read through it if you have any questions about how things work in Cafe. And just to give you a flavor, on the left here, this shows you, this defines the net parameter, which is the type of protocol buffer that Cafe uses to represent nets. And on the right is this solver parameter, which Cafe uses to represent solvers. So the net parameter, so the solver parameter, for example, takes a reference to a net, and it also includes things like learning rate and how often to checkpoint and other things like that. Right, so when you're working in Cafe, actually, it's pretty cool. You don't need to write any code in order to train models. So when working with Cafe, you generally have this 4-step process. So first, you'll convert your data. And especially if you just have an image classification problem, you don't have to write any code for this. You just use one of the existing binaries that Cafe ships with. Then you'll define your net file that you'll do by just writing or editing one of these proto.txts. Then you'll define your solver, which again will just be a proto.txt text file that you can just work with in a text editor. And then you'll pass all of these things to this existing binary to train the model. and that'll spit out your trained Caffe model to disk that you can then use for other things. So even if you wanted to train ResNet on ImageNet, you could just follow this simple procedure and train a giant network without writing any code. So that's really cool. And so step one, generally, you'll need to convert your data. So Caffe uses, I know we've talked a little bit about HDF5 as a format for storing pixels on disk contiguously and then reading from them efficiently. But by default, Caffe uses this other file format called LMDB. So if all you have is a bunch of images, each image with a label, then you can then Caffe just has a script to convert that whole data set into a giant LMDB that you can use for training. So just to give you an idea, this is really easy. You just create a text file that has the path to your images and separated by the label, and you just pass it to your Caffe script. Wait a couple hours if your data set's big, and you end up with a giant LMDB file on disk. And if you're working with something else like HDF5, then you'll have to create it yourself, probably. So Caffe does actually have a couple other options for reading data in. There's this data layer, window data layer for detection. It actually can read from HDF5. And there's an option for reading stuff directly from memory that's especially useful with the Python interface. But at least in my point of view, all of these types of other methods of reading in data to Caffe are a little bit second-class citizens in the Caffe ecosystem. And LMDB is really the easiest thing to work with. So if you can, you should probably try to convert your data into LMDB format with Caffe. So step 2 for Caffe is to define your net object. So like I said, you'll just write a big proto-txt to define your net. So here, this just defines a simple model for logistic regression. You can see that I did not follow my own advice, and I'm reading data out of an HDF5 file here. Then I have a fully connected layer, which is called inner product in Caffe. So that's fully connected layer tells you the number of classes and how to initialize the values. And then I have a softmax loss function that reads the labels and produces loss and gradient from the outputs of the fully connected layer. So a couple of things to point out about this file are that one, every layer typically includes some blobs, which to store the data and the gradients and the weights. And the layers, blobs, and the layer itself typically have the same name. So that can be a little bit confusing. Another thing is that a lot of these layers will have 2 blobs, one for weight and one for bias. And actually, in this right in here, you'll define the learning rates for those 2 blobs. So that's learning rate and regularization for both the weight and the bias of that layer. Another thing to note is that to specify the number of output classes is just the num output on this fully connected layer parameter. And finally, the quick and dirty way to freeze layers in Caffe is just to set the learning rate to 0 for the blobs associated to that layer's weights or biases. Another thing to point out is that for ResNet and other large models like GoogleNet, this can get really out of hand really quickly. So Caffe doesn't really let you define compositionality. So for ResNet, they just repeat the same pattern over and over and over in the proto-txt file. So the ResNet proto-txt is almost 7,000 lines long. So you could write that by hand, but in practice, people tend to write little Python scripts to generate these things automatically. So that's a little bit gross. If you want to fine-tune a network rather than starting from scratch, then you'll typically download some existing proto-txt and some existing weights file and work from there. So the way you should think about it is that the proto-txt file that we've seen here before defines the architecture of the network. And then the pre-trained weights live in this .caffe model file. That's a binary thing, and you can't really inspect it. But the way that it works is it's basically key value pairs, where it matches inside the Caffe model, it matches these names that are scoped to layers. So this fc7.weight would be the weight corresponding to this final fully connected layer in AlexNet. So then when you want to fine-tune on your own data, when you start up Caffe and you load a Caffe model and a proto-txt, it just tries to match the key value pairs of names and weights between the Caffe model and the proto-txt. So if the names are the same, then your new network gets initialized from the values in the proto-txt, which is really, really useful and convenient for fine-tuning. But if the names don't match, then those layers actually get initialized from scratch. So this is how, for example, you can reinitialize the output layer in Caffe. So to be a little bit more concrete, if you've maybe downloaded an ImageNet model, then this layer is this final fully connected layer that's outputting class scores will have 1,000 outputs. But now maybe for some problem you care about, you only want to have 10 outputs. So you're going to need to reinitialize that final layer and reinitialize it randomly and fine-tune the network. So the way that you do that is you need to change the name of the layer in the proto.txt file to make sure that it's actually initialized randomly and not reading from the cafe model. And if you forget to do this, then it'll actually crash. And it'll give you a weird error message about the shapes not aligning. Because it'll be trying to store this 1,000-dimensional weight matrix into this 10-dimensional thing from your new file, and it won't work. So the next step when working with Caffe is to define the solver. The solver is also just a proto.txt file. You can see all the options for it in that giant.proto file that I gave a link to. But it'll look something like this for AlexNet maybe. So that will define your learning rate and your learning rate decay and your regularization, how often to checkpoint, everything like that. But these end up being much less complex than these proto.txts for the networks. This AlexNet guy is just maybe 14 lines. Although what you will see sometimes in practice is that if people want to have sort of complex training pipelines, where they first want to train with one learning rate in certain parts of the network, and then they want to train with another learning rate, certain parts of the network, that you might end up with a cascade of different solver files and actually run them all independently, where you're sort of fine-tuning your own model in separate stages using different solvers. So once you've done all that, then you just train your model. So if you followed my advice and just used LMDB and written all these things, then you just call this binary that exists in Caffe already. So here you just pass it your solver and your proto.txt and your pre-trained weights file if you're fine-tuning. And it'll run maybe for a day, maybe for a long time, and just checkpoint and save things to disk, and you'll be happy. One thing to point out here is that you specify which GPU it runs on. This is 0 indexed. But you can actually run in CPU-only mode by setting this flag to -1. And actually, sometime in the last year, Caffe added data parallelism to let you split up mini batches across multiple GPUs in your system. So you can actually add multiple GPUs on this flag. And if you just say all, then Caffe will automatically split up mini batches across all the GPUs on your machine. So that's really cool. You've done multi-GPU training without writing a single line of code. Pretty cool. Caffe, oh yeah, question?
What if I want to initialize two sort of parallel networks with the same path and
Yeah, I think that'll be kind of, so the question is how would you go about doing some more complex initialization strategy where you maybe want to initialize the weights from a pre-trained model and use those same weights in multiple parts of your network. And the answer is that you probably can't do that with a simple mechanism. You can kind of munge around the weights in Python, and that's probably how you'd go about doing it. Right, so I think we've mentioned this before, that Caffe has this really great model zoo, where you can download lots of different types of pre-trained models on ImageNet and other data sets. So this model zoo is really top-notch. You've got AlexNet and VGG. You've got ResNets up there already. Pretty much lots and lots of really good models are up there. So that's a really, really strong point about Caffe, that it's really easy to download someone else's model and run it on your data or fine-tune it on your data. Caffe has a Python interface, like I mentioned. Since there's so many things to cover, I don't think I can dive into detail here. But as is kind of par for the course in Caffe, there's not really, really great documentation about the Python interface. So you need to read the code. And the Python interface for Caffe is mostly defined in these two files. This CPP file uses Boost Python, if you've ever used that before, to wrap up some of the C++ classes and expose them to Python. And then in this .py file, it actually attaches additional methods and gives you a more Pythonic interface. So if you want to know what kinds of methods and data types are available in the Caffe Python interface, your best bet is to just read through these two files. And they're not too long, so it's pretty easy to do. Yeah, so the Python interface in general is pretty useful. It lets you do maybe crazy weight initialization strategies if you need to do something more complex than just copy from a pre-trained model. It also makes it really easy to just get a network and then run it forward and backward from NumPy arrays. So for example, you can implement things like Deep Dream and class visualizations, similar to that you did on the homework. You can also do that quite easily using the Python interface on Caffe, where you just need to take data and then run it forward and backward through different parts of the network. The Python interface is also quite nice if you just want to extract features. Like you have some data set, you have some pre-trained model, and you want to extract features from some part of the network, and then maybe save them to disk, maybe to an HDF5 file for some downstream processing. So that's quite easy to do with the Python interface. You can also, actually Caffe has a kind of a new feature where you can actually define layers entirely in Python. But this is, I've never done it myself, but it seems cool, it seems nice. But the downside is that then those layers will be CPU only. So we talked about communication bottlenecks between the CPU and the GPU, that if you write layers in Python, then every forward and backward pass, you'll be incurring overhead on that transfer. Although one nice place where Python layers could be useful is custom loss functions. So that's maybe something that you could keep in mind. So the quick overview of Caffe pros and cons is that really from my point of view, if all you want to do is kind of train a simple basic feed-forward network, especially for classification, then Caffe is really, really easy to get things up and running. You don't have to write any code yourself. You just use all these pre-built tools, and it's quite easy to run. It has a Python interface, which is quite nice for using a little bit more complex use cases. But it can be cumbersome when things get really crazy. When you have these really big networks like ResNet or GoogleNet, especially with repeated module patterns, it can be tedious. And for things like RNet, like recurrent networks, where you want to share weights between different parts of the network, can be kind of cumbersome in Caffe. It is possible, but it's probably not the best thing to use for that. And the other big downside from my point of view is that when you want to define your own type of layer in Caffe, you end up having to write C++ and CUDA code. So doesn't give you a very quick development cycle. So it's kind of painful to write new layers in Caffe. So that's our whirlwind tour of Caffe. So if there's any quick questions, yeah.
How would you do something like cross-validation?
Cross-validation in Caffe? So in the train val proto.txt, you can actually define a training phase and a testing phase. So generally, you'll write like a train val proto.txt and a deploy proto.txt. And the deploy will be used on the test set. And the test phase of the train val proto.txt will be used for validation. OK, that's all there is to know about Caffe. So the next one is Torch. So Torch is really my personal favorite. So I have a little bit of bias here, just to get that out in the open, that I've pretty much been using Torch almost exclusively for my own projects in the last year or so. So Torch is originally from NYU. It's written in C and in Lua. And it's used a lot at Facebook and DeepMind especially. I think also a lot of folks at Twitter use Torch. So one of the big things that freaks people out about Torch is that you have to write in Lua, which I had never heard of or used before starting to work with Torch, but it actually isn't too bad. That Lua is this high-level scripting language that is really intended for embedded devices, so it can run very efficiently. And it's very similar to JavaScript in a lot of ways. So another cool thing about Lua is that because it's meant to be run on embedded devices, that you can actually do for loops are really fast in Torch. You know how in Python, if you write a for loop, it's going to be really slow? That's actually totally fine to do in Torch, because it actually uses just-in-time compilation to make these things really fast. And Lua is most similar to JavaScript in that it is a functional language. Functions are first-class citizens, and it's very common to pass callbacks around to different parts of your code. Lua also has this idea of prototypical inheritance, where there's sort of one data structure, which in Lua is a table, which you can think of as being very similar to an object in JavaScript. And you can implement things like object-oriented programming using prototypical inheritance in a similar way as you would in JavaScript. And one of the downsides is actually the standard library in Lua is kind of annoying sometimes, and things like handling strings and whatnot can be kind of cumbersome. And maybe most annoying is that it's one-indexed. So all of your intuition about for loops will be a little bit off for a while. But other than that, it's pretty easy to pick up. And I gave a link here to this website claiming that you can learn Lua in 15 minutes. It might be a little bit of an they might be overselling it a little bit, but I think it is pretty easy to pick up Lua and start writing code in it pretty fast. So the main idea behind Torch is this tensor class. So you guys have been working in NumPy a lot on your assignments. And the way the assignments are kind of structured is that the NumPy array gives you this really easy way to manipulate data in whatever way you want. And then you can use that NumPy array to build up other abstractions like neural net libraries and whatnot. But really, the NumPy array just lets you manipulate data numerically in whatever way you want in complete flexibility. So if you recall, then maybe here's an example of some NumPy code that should be very familiar by now, where we're just computing a simple forward pass of a 2-layer ReLU network. So maybe black wasn't the best choice here, but we're computing some constants, we're computing some weights, we're getting some random data, and we're doing a matrix multiply, a ReLU, and another matrix multiply. So that's very easy to write in NumPy. And actually, this has almost a one-to-one translation into Torch tensors. So now on the right, this is the exact same code, but using Torch tensors in Lua. So here, we're defining our batch size, input size, and all that. We're defining our weights, which are just Torch tensors. We're getting a random input vector. We're doing a forward pass. This is doing a matrix multiply of Torch tensors. This Cmax is an element-wise maximum, so that's a ReLU. And then we can compute scores using another matrix multiply. So in general, pretty much any kind of code you're used to writing in NumPy is pretty easy, pretty much has almost a one-by-one, line-by-line translation into using Torch tensors instead. So you'll also remember in NumPy that it's really easy to swap and use different data types. We talked about this ad nauseum in the last lecture, but at least in NumPy, to switch to maybe a 32-bit floating point, all you need to do is cast your data to this other data type. And it turns out that that's very, very easy to do in Torch as well. That our data type is now this string, and then we can easily cast our data to another data type. But so this next slide is the real reason why Torch is infinitely better than NumPy. And that's that the GPU is just another data type. So when you want to run code on the GPU in Torch, you import another package. And you have another data type, which is torch.CUDA tensor. And now you cast your tensors to this other data type. And now they live on the GPU. And running any kind of numerical operations on CUDA tensors just runs on the GPU. So it's really, really easy in Torch to just write generic tensor scientific computing code to run on a GPU and be really fast. So this, like I said, these tensors are really, you should think of them as similar to NumPy arrays. And there's a lot of documentation on the different kinds of methods that you can work with in tensors up here on GitHub. This documentation isn't super complete, but it's not bad, so you should take a look at it. So but in practice, you end up not really using the tensors too much in Torch. Instead, you use this other package called NN for neural networks. So NN is this pretty thin wrapper that actually defines a neural network package just in terms of these tensor objects. So you should think of this as being like a beefier, more industrial strength version of the homework code base, where you have this ND array, this tensor abstraction, and then you implement a neural net library on top of it in a nice, clean interface. So here's this same 2-layer ReLU network using the NN package. So we define our network as a sequential. So it's going to be a stack of sequential operations. We're going to first have a linear, which is a fully connected layer from our input dimension to our hidden dimension. We're going to have a ReLU and another linear. Now we can actually get the weights and gradients in one tensor for each using this get parameters method. So now weights will be a single Torch tensor that will have all the weights of the network, and grad weights will be a single Torch tensor for all of the gradients. We can generate some random data. Now to do a forward pass, we just call net the forward method on the net object using our data. And this gives us our scores. To compute our loss, we have a separate criterion object that is our loss function. So we compute our loss by calling the forward method of the criterion. Now we've done our forward pass, very easy. And for our backward pass, we first set our gradients to 0, call a backward on the loss function, and then a backward on the network. Now this has updated all of the gradients for the network in the grad params, so we can just make a gradient step very easily. So this would be multiplying the grad weights by the opposite of the learning rate, and then adding it to the weights. So that's a simple gradient descent update. Right, so that's all of the Right, so that would have been maybe a little bit more clear, but we have a net, we have weights, grad weights, we have our loss function, we get random data, run forward, run backward, make an update. And as you might expect from looking at the tensor, it's quite easy to make this thing run on GPU. So to run one of these networks on the GPU, we import a couple new packages, cuTorch and cuNN, which are CUDA versions of everything. And then we just need to cast our network and our loss function to this other data type. And we also need to cast our data and labels. And now this whole network will run and train on the GPU. So it's pretty easy. Now in, what is that, like 40 lines of code, we've written a fully connected network, and we can train it on the GPU. But one problem here is that we're just using vanilla gradient descent, which is not so great. And as you saw in the assignments, other things like Atom and RMS prop tend to work much better in practice. So to solve that, Torch gives us the Optim package. So Optim is quite easy to use. Again, we just import a new package up here. And now what changes is that we actually need to define this callback function. So before, we were just calling forward and backward explicitly ourselves. Instead, we're going to define this callback function that will run the network forward and backward on data, and then return the loss and the gradient. And now to make an update step on our network, we'll actually pass this callback function to this Atom method from the Optim package. So this is maybe a little bit awkward, but now we can use any kind of update rule using just a couple lines of change from what we had before. And again, this is very easy to add to run on a GPU by just casting everything to CUDA. Right, so as we saw in Caffe, Caffe sort of implements everything in terms of nets and layers. And Caffe has this really hard distinction between a net and a layer. In Torch, we don't really draw this distinction. Everything is just a module. So the entire network is a module, and also each individual layer is a module. Modules are just classes that are defined in Lua that are implemented using the Tensor API. So these modules are, since they're written in Lua, they're quite easy to understand. So linear is the fully connected the fully connected layer in Lua, and this is the constructor. You can see it's just setting up tensors for the weight and the bias. And because this Tensor API in Torch lets us easily run the same code on GPU and CPU, then all of these layers will just be written in terms of the Tensor API and then easily run on both devices. So these modules need to implement a forward and backward. So for forward, they decided to call it update output. So here's the example of the update output for the fully connected layer. There's actually a couple cases. They need to deal with a couple different cases here to deal with mini batch versus non-mini batch inputs. But other than that, this should be quite easy to read. For the backward pass, there's a pair of methods, update grad input, which receives the upstream gradients and computes the gradients with respect to the input. And again, this is just implemented in the Tensor API. So it's very easy to understand. It's just the same type of thing you saw in the homework. And we also implement an accumulate grad parameters, which computes the gradients with respect to the weights of the network. As you saw in the constructor, the weights and the biases are held in instance variables of this module. And accumulate grad parameters will receive gradients from upstream and accumulate gradients of the parameters with respect to the upstream gradients. And again, this is very simple, just using the Tensor API. So Torch actually has a ton of different modules available. The documentation here can be a little bit out of date, but if you just go on GitHub, you can see all the .lua files that give you all the goodies to play with. And these actually get updated a lot. So just to point out a couple, these three were just added in the last week. So Torch is always adding new modules that you can add to your networks, which is pretty fun. But when these existing modules aren't good enough, it's actually very easy to write your own. So because you can just implement these things using the Tensor API and just implement the forward and backward, it's not much harder than implementing layers on the homeworks. So here's just a small example. This is a stupid module that just takes its input and multiplies it by 2. And you can see we implement the update output and the update grad input. And now we've implemented a new layer in Torch in just 20 lines of code. And then that's really easy. And then it's very easy to use in other code. Just import it, and now you can add it to networks and so on. And the really cool thing about this is because this is just the Tensor API, you can do whatever kind of arbitrary thing you want inside of these forward and backward. If you need to do for loops or complicated imperative code or maybe stochastic things for dropout or batch normalization, then whatever kind of code you want on the forward and backward pass, you just implement it yourself inside these modules. So it's usually very easy to implement your own new types of layers in Torch. So Torch, but of course, using individual layers on their own isn't so useful. We need to be able to stitch them together into larger networks. So for this, Torch uses containers. We already saw one in the previous example, which was this sequential container. So a sequential container is just a stack of modules where one receives the output from the previous one and just goes in a linear stack. So that's probably the most commonly used. Another one you might see is this concat table. So maybe if you have an input and you want to apply two different modules to the same input, then the concat table lets you do that, and you receive the output as a list. Another one you might see is a parallel table. If you have a list of inputs and you want to apply different modules to each element of the list, then you can use a parallel table for that sort of a construction. But when things get really complicated, so actually those containers that I just told you should, in theory, be possible to implement just about any topology you want. But it can be really hairy in practice to wire up really complicated things using those containers. So Torch provides another package called nngraph that lets you hook up things in more complicated topologies pretty easily. So here's an example. If we have 3 inputs and we want to produce 1 output, and we want to produce them with this pretty simple update rule, that corresponds to this type of computational graph that we've seen many times in lecture for different types of problems. So you could actually implement this just fine using parallel and sequential and concat table, but it could be kind of a mess. So when you want to do things like this, it's very common to use nngraph instead. So this nngraph code is quite easy. So here this function is going to build a module using nngraph and then return it. So here we import the nngraph package. And then inside here, this is a bit of funny syntax. So this is actually not a tensor. This is defining a symbolic variable. So this is saying that our tensor object is going to receive x, y, and z as inputs. And now here, we're actually doing symbolic operations on those inputs. So here we're saying that we want to have a pointwise addition of x and y, store that in A. We want to have pointwise multiplication of A and Z and store that in B. And now pointwise addition of A and B and store that in C. And again, these are not actual tensor objects. These are now sort of symbolic references that are being used to build up this computational graph in the back end. And now we can actually return a module here where we say that our module will have inputs x, y, and z and outputs c. And this nn.g module will actually give us an object conforming to the module API that implements this computation. So then after we build the module, we can construct concrete Torch tensors and then feed them into the module that will actually compute the function. So Torch actually is quite good at pre-trained models. There's a package called Load Cafe that lets you load up many different types of pre-trained models from Cafe, and it'll convert them into their Torch equivalents. So you can load up the Cafe proto.txt and the Cafe model file, and it'll turn into a giant stack of sequential layers. Load Cafe is not super general, though, and only works for certain types of networks. But in particular, Load Cafe will let you load up AlexNet and CafeNet and VGG. So those are probably some of the most commonly used. There are also a couple different implementations that let you load up GoogleNet into Torch to let you load up pre-trained GoogleNet models into Torch. And actually, very recently, Facebook went ahead and re-implemented the residual networks straight up in Torch. And they released pre-trained models for that. So between AlexNet, CafeNet, VGG, GoogleNet, and ResNet, I think that's probably everything you need, all the pre-trained models that most people want to use. Another point is that because Torch is using Lua, we can't use pip to install packages. And there's a very similar idea called Lua Rocks that lets you easily install new packages and update packages. And that's very, very easy to use. And this is kind of just a list of some packages that I find very useful in Torch. So there are cuDNN bindings. You can read and write to HDF5 files. You can read and write JSON. There's this funny one from Twitter called Autograd that is a little bit like Theano, which we'll talk about in a bit. but I haven't used it, but it's kind of cool to look at. And actually, Facebook has a pretty useful library for Torch as well that implements FFT convolutions and also implements data parallel and model parallelism. So that's a pretty nice thing to have. So a very typical workflow in Torch is that you'll have some pre-processing script, often in Python, that'll pre-process your data and dump it onto some nice format in disk. Usually HDF5 for big things and JSON for little things. Then I'll typically write a train.lua that'll read from the HDF5 and train the model and optimize the model and save checkpoints to disk. And then usually I'll have some evaluate script that loads up the trained model and then does it for something useful. So a case study for this type of workflow is this project I put up on GitHub like a week ago that implements character-level language models in Torch. So here, there's a pre-processing script that converts text files into HDF5 files. There's a training script that loads from HDF5 and trains these recurrent networks. And then there's a sampling script that loads up the checkpoints and lets you generate text. So that's kind of like my typical workflow in Torch. So the quick pros and cons I would say about Torch are that it's Lua. This is a big turnoff for people, but I don't think it's actually that big a deal. It's definitely less plug and play than Caffe. So you'll end up writing a lot of your own code typically, which maybe is a little bit more overhead, but also gives you a lot more flexibility. It has a lot of modular pieces that are easy to plug and play. And the standard library, because it's all written in Lua, is quite easy to read and quite easy to understand. There's a lot of pre-trained models, which is quite nice. But unfortunately, it's a little bit awkward to use for recurrent networks in general. So when you want to have multiple modules that share weights with each other, you can actually do this in Torch, but it's kind of brittle, and you can run into subtle bugs there. So that's probably the biggest caveat, is that recurrent networks can be tricky. Any quick questions about Torch? Yeah.
Well, you mentioned that it's efficient to run for loops. So are you saying, for example, in our convolutional net layer, we used to have 4 layers in the naive version, and in the fast one, you just call. So do you still gain any benefit to?